In this lecture, we will solve numerical on rotor design of a three-phase induction motor, and the numerical is find the current in the bars and end rings of a cage rotor of a 6-pole 3-phase induction motor having 72 stator slots with 15 conductor in each slot. If the stator current per phase is 20 ampere and rotor slots are 55, hence find the suitable size of the cage bars and end rings. Now if you read this example, then in this example it is asked to calculate the four different quantities. The first is the current in the bars and end rings. It means we need to calculate the current in the rotor bar, that is IB, and current in the end ring, that is IE. Along with this, we need to find the size of cage bars, that is bar size AB and size of the end ring, that is AE. So these four quantities we need to calculate, and to calculate these quantities the data given is number of poles are 6, having a stator slots 72. So stator slots are denoted by SS. So SS is 72, and the conductors in each slots are 15. So that is ZS. So the ZS is the number of conductors in each slot, and the stator current is also given, that is IS, that is the stator current per phase. Along with that, the rotor slots are also given, and that is SR is equals to 55. Now let me solve this example. First we will calculate the current in the rotor bar, that is IB, and the IB is calculated by the expression 0.85 into 6 into IS into TS divided by SR. Now in this expression, if you check the given data, then the IS is given and SR is also given, but the TS value is not given, where the TS is the number of turns per phase of the stator, and this TS can be calculated by using the EMF equation. But if you want to calculate the TS by using the EMF equation, then the voltage and flux information must have been given. But if you read this example and if you see the given data, then the given data is not having data related with the voltage and the flux. So we are calculating here the number of turns per phase of the stator by using the information about the stator slots and the number of conductors in each stator slot. So how to calculate the turns per phase? Now to calculate the turns per phase, the total number of slots are given 72, and in every slot the 15 conductors are housed. As we know that the total stator winding is housed in the all slots. So how many stator conductors are there? If in one slot 15 conductors are there, then obviously in the 72 conductors, the number of 72 slots, the number of conductors becomes 72 into 15. Now these are the total number of conductors of the stator winding, and we know that the every turn is having the two conductors. So the total turns consist by the stator winding becomes 72 into 15 divided by 2. So these many turns are used in the all three phases. Now if you want to calculate here the number of turns per phase, then you have to divide by the number of phases. So just we are dividing here by the number of phases 3. So we are getting here the number of turns per phase of the stator, and if you calculate this, you will get 180. So here the number of turns per phase of the stator are 180. Now we will put this value of the TS in the equation of the bar current. Then we will get here the rotor bar current is 0.85 into 6 into 20 is the IS, and 180 is the TS, and 55 is the SR. So after calculating this, we will get 333.8 ampere. So the rotor bar current value is 333.8 amperes. Now let me calculate the size of the rotor bar, that is AB. As we know that the expression of the size of the rotor bar AB is the ratio of IB and current density del B. And here the IB we have already calculated in the previous step as the IB is equals to 333.8 ampere. So we required here the current density of the rotor bar. But if you see the given data, then in the given data the current density is not given, and as I already told in the previous lecture, if the current density is not given, then you can assume the current density of the rotor bar between 4 to 7 ampere per millimeter square. So here, because of the current density is not given in the example, let me assume the current density as 5 ampere per millimeter square. And if you assume this value, then by using this expression, we can calculate the size of the rotor bar is IB, that is 333.8 divided by the current density del B, which is 5 ampere per millimeter square. Then we get 66.76 millimeter square. So this is the size of rotor bar at assumed current density. Now the next quantity is the current in the end ring, and the expression for the current in the end ring is SR into IB divided by pi into P. So in this expression, SR is already given, that is 55. IB we have calculated in the previous steps as 333.8 divided by pi, and number of poles P are given 6. So by simply inserting these values in the equation of the IE, we get 973.4 ampere. So the current in the end ring is 973.4 amperes. And the next quantity is size of the end ring. So similar to the size of the rotor bar, the size of end ring is also calculated by using the expression, the ratio of the current in the end ring to the density of the end ring. So the current in the end ring we have calculated as 973.4 and the current density of the end ring is not given. So again, in the previous lecture I have told you, if the current density of the end ring is not given, then you can assume between the 4 to 8 ampere per millimeter square. So let me assume here the current density is 7 ampere per millimeter square. Then if you insert this value in the expression of the size of the end ring, then we get the equation 973.4, that is current in the end ring, divided by 7, that is the current density, and it becomes 139 millimeter square. So the size of end ring becomes 139 millimeter square. So these four quantities are asked in this example, and we have calculated all four asked quantities. Now similar kind of two examples I have given in the exercise. This is example number 1 and this is the example number 2. So solve these examples as a practice at home. Thanks for watching.